Would like now to show an important property of the intensity, and that the intensity is constant along a ray. Now, this doesn't seem to be the case here because, as you're seeing, you have a solid angle, and the beams they are spreading out. If it is spreading out, you imagine that the energy of a single beam is not constant because, as this spreads with distance, this area becomes bigger and bigger. So, just like the flux, you would expect it to decrease with the distance. But the intensity is in fact constant with distance, unlike the flux. And that is actually the reason why the intensity is the fundamental quantity of the radiation field. It's the energy that you would expect a single photon to have, and photons do not spread. You can see this property, this counterintuitive property. It will occur when we take the limit of the solid angle going to zero, and in that limit, the beam will stop spreading out. Essentially, what you're doing as you decrease the solid angle is that you're capturing less and less rays in the beam. And eventually, when the solid angle is infinitesimal, you would be capturing a single ray. Now, due to energy conservation, the energy is constant along the ray, and thus the intensity does not depend on the distance. So let's prove this. Now, that is an interesting property. That means that even though the flux that you get from the sun is different at the different distances at the different planets, the brightness of the disk of the sun is the same, is independent of distance. If you look at the distance of the sun, every single patch, every single area on the disk of the sun would look equally bright. This might sound counterintuitive until you realize that a white wall does not get brighter as you approach it. So to prove this, consider 2 points, P1 and P2, along a ray. They are separated by a distance r. And consider that the energy that leaves P1 and reaches P2. So these locations are points, so they do not fit our macroscopic definitions. What we're going to do is that we're going to construct an area around P1, that's the area dA1. This area is emitting radiation. And then you construct an area dA2 around P2 that will detect this radiation. So these are the areas dA1 and dA2. Now consider the solid angle d omega 1, which is this one, that goes from P1 to the area dA2. Now the energy flowing from the area dA1 around P1 into the solid angle that crosses dA2 is going to be given by the energy is equal to the intensity at the point 1 times the area dA1 times the solid angle d omega 1 times the infinitesimal interval of time that the event takes place. So dE is equal to I dA d omega dt. Now, what is the intensity I2 that is measured at P2? From the point of view of P2, it is collecting radiation with an area dA2. The emitting source, which is of area dA1, is seen from P2 at a distance r, forming a solid angle d omega 2. Now P2 is measuring an amount of energy, dE2, which is equal to the intensity times the area times the solid angle times the time. Let us assume that the intensity is different and call it I2. Now it's collecting this energy with an area dA2, seen from a solid angle d omega 2, and in an interval of time dt. Now, because the energy is conserved, then d1 is equal to d2. Now, substituting the definition of the solid angle, d omega 1 is the area dA2 seen from a distance r. So that is equal to dA2 over r squared. And d omega 2 is the area dA1 seen from a distance r. So it is dA1 over r squared. Substituting these definitions then, so you can cut to the dA1, dA2, and r squareds, and then you have that I1 is equal to I2. So the intensities of P1 and P2 are equal. The reason for this is simple, as we stated before. As we make the solid angle d omega infinitesimal, we can in principle make the beam so narrow that only a single photon can fit in its width. And because a photon does not spread its energy as it travels, the energy in the beam does not dilute with distance. So we see the reason why the surface of the sun is as bright seen from Earth as is seen from Neptune. Intensity is an intrinsic property of resolved sources of radiation. As long as you resolve a source of radiation, the intensity that you measured from a point on that surface is going to be constant. Is when you start not resolving it, when the solid angle of your detector is bigger than the solid angle of the source, that you start measuring flux.